Welcome back. Welcome back to the atmospheric lecture for Earth Science Part 2. In the previous Part 1, we looked at some characteristics of the atmosphere. We looked at the layers that compose the atmosphere: troposphere, stratosphere, mesosphere, thermosphere. All these layers of the atmosphere are separated or delineated by temperature changes. We looked at the composition of the atmosphere: 78% nitrogen, about 21% oxygen. We also looked at the electromagnetic spectrum and covered the elementary principles of the EM scale and how the atmosphere reacts to the insolation or incoming solaration that penetrates the atmospheric layers. So we're now going to switch gears and focus on water. And we know from the previous Part 1 that the atmosphere is made up of 1 to 4% water vapor. And so we're going to find that water vapor, or water in general, is very instrumental in the various processes that take place within the atmosphere. So to start off with, on this first slide, we're looking at the natural forms of moisture in the atmosphere. And we see here that we have ice, water, and vapor, which represents one of the most remarkable substances on Earth. In fact, Earth is really the only planet in which water can exist in all three states. So it exists as an ice, liquid water, and vapor. And just for clarification purposes, then we would call ice a solid, water a liquid, and of course the vapor, we can call it a gas. So for the next several slides, we're going to kind of look at what the role of water in the various phases are within the Earth's atmosphere, which is activities and processes that we feel. So to start with, we need to kind of take a look at how nature transfers water from one phase to the next phase. And so you're looking at a diagram in which it's showing molecules of water in this case, and we're looking at how those molecules are structured. So for example, in ice or a solid, we can see that the molecules are very tightly packed together, very close together. There's no arrows on the molecules in this case for ice, because that's a symbol that the molecules are stationary, they're not moving. Then we move up to the liquid, and here the amount of space between the particles get a little bit less. They open up, and these little tiny arrows on each one of these particles indicate that these are moving particles. The arrows are small, so it's just more or less move slow, and that would be typical of a liquid. For example, if you pour liquid water on a table, it'll kind of, the molecules will kind of roll over one another and create that movement. Then the next diagram up here is water vapor, and here you can see that the arrows are a little bit larger on each one of the molecules, which is indicating that those molecules move pretty fast. So they move very randomly, and they move fast. And so they're moving a lot faster than water, and then the ice, in this case solid, isn't moving at all. So the question is, what allows a phase change, for example, between a solid and a liquid and a vapor? And in this case, water. So we need to analyze the energy. We need to analyze energy moving into the system and energy moving out of the system. So if you look to your left here, there's an arrow that's moving from a vapor to a liquid to a solid. And here we say that we're moving from a less ordered state, which would be represented by the vapor, moving towards a more ordered state. In order for nature to achieve a more ordered state, then energy is going to move out. So we would say from a vapor to a liquid, energy is moving out. From a liquid to a solid, energy is moving out. And so really, if you kind of look at this on this diagram, it really says this: the more energy that's in a system, the more rapid that the particles are going to move, and that's with water vapor. Take a little energy out of it, it's going to slow down, make a liquid. Take most of the energy out of it, now it then becomes a solid. Particles aren't moving at all. And so if we're moving energy out, we can do the opposite, and we can move energy in. So if you look now at the right-hand side of your screen, the pink line, here we say that energy is being taken in. And so we start with the solid or the ice. We add a little energy to it. Now it becomes a liquid. And we add more energy to the liquid, and now it becomes vapor. And a good analogy for this would be taking ice, for example. So we come back to ice. What happens when you start putting heat or a little energy into ice? It begins to melt. And as the ice melts, it now becomes a liquid, so it has more energy. And now you take liquid water and you boil the water, and it reaches a particular temperature. It has more energy, and now the water begins to give off steam, or in this case, water vapor. So various processes within the atmosphere will allow phase changes to take place between ice, liquid, and water vapor. And every time there's a phase change, then energies, again, move out or in. And so that energy, either moving in or out, drives various processes within the atmosphere. And so we're going to refer to this energy being either released or absorbed. We're going to refer to this as what we call latent heat. So you come down here and you look at latent heat. Latent heat represents a type of hidden heat, represents the amount of heat either released or absorbed during a phase change. And again, within the atmosphere, when there's a phase change, that heat either is absorbed or released, but has to go somewhere, which ends up ultimately driving the processes that we feel in the atmosphere today. So it's your job as earth science students to study this and get a real handle on what it means to be latent heat. Because again, as we go through some of these processes, we're going to talk about where that latent heat is either being absorbed or it's being released. So this is a diagram here that kind of applies a couple of terms that we've already familiar with, but this time we're going to apply it with respect to latent heat. So for example, we can take the ice right here, the solid. We can absorb heat or add heat to the ice, and again, it melts to liquid water. But the word that we're familiar with is evaporation. And so we can take liquid water, allow the sun to radiate on this liquid water. For example, you can kind of envision a puddle of water. And as the sun heats up that puddle of water, that puddle goes away. But does it really? And the answer is it really doesn't go away, because it's evaporated and it moves from the liquid phase through evaporation to the gaseous phase. So in fact, when water does evaporate off the puddle of a sidewalk, it really now is putting vapor or water vapor back into the atmosphere. And conversely, we can take the vapor, and once we cool that vapor or allow heat to be released, then we move from a vapor and we move it back into a liquid, and heat then again is being released, and we call that condensation. And so those are two terms, evaporation and condensation, that I'm sure we've heard throughout our time. But now we're going to put some type of latent heat concept behind it. So evaporation is where heat is absorbed. Condensation is where heat is released. And these two processes, evaporation and condensation, drive, again, various processes that we feel in our atmosphere. So here are some examples of latent heat. So this first example, it says water is evaporated off your skin surface and you feel cool. Why does that happen? So this is an analogy where you get out of the shower or you get out of the pool, and regardless of what the ambient temperature is, you'll always feel cooler. And that is that water is being evaporated. Water is being evaporated off of your skin surface, therefore absorbing the heat from your body. And so you feel cooler. And so you're really moving from a liquid state to the vapor state. And of course, if you're in Bakersfield summer and you're in the pool and you get out of the pool, you feel cooler only for a while, because once that water is evaporated off of your skin, then it can't take the heat out of your body anymore, and therefore you're going to get warm again. So that's a pretty good example of latent heat being absorbed. In this next example, this is where we're going to use latent heat to form clouds. And we're going to form clouds through the process of condensation. In other words, we're going to change the water vapor to a suspended liquid. And so again, we're going to find out there are several processes in the atmosphere that allows water vapor to cool. And as that water vapor cools, it will then move from the vapor phase to the liquid phase through condensing. And then what's going to happen with the latent heat? Is it released or is it absorbed? The answer is the latent heat is released. So when clouds are forming, energy is actually being released. So if you look at the bottom of the screen, the next question is, where does the latent heat go? So this slide here kind of introduces us now to various types of processes that take place within our atmosphere. So that absorbed and released latent heat is circulated throughout the Earth's atmosphere. And that circulation of this latent heat, this hidden heat, then gives rise to clouds, gives rise to various forms of precipitation, gives rise to humidity, mugginess. It gives rise to a whole host of experiences that we've had in the atmosphere of what we felt. So for the rest of the discussion, we're going to focus on humidity. We're going to focus on the greenhouse effect, and we're going to focus on a process known as adiabatic processes. And we'll look at convection within the atmosphere, and finally this word condensation, which we've touched on a little bit. So let's look at humidity. And the question is, how do you feel on a hot, humid day? And most of the time when I ask this question to the classes, it's overwhelmingly decided that on a hot, humid day, one feels sticky, you're constantly perspiring, you're always wet. The old thing is that you take a shower, you get out and dry yourself, and you're already wet again. Or sometimes in humid evenings and at nighttime, it's very difficult to sleep at night. Some folks have fans and just sleep in sheets. So it's a very, in most incidences, it's a very uncomfortable situation to be in. So what is humidity? So humidity is defined by how much water vapor is present in the atmosphere. And so if you have lots and lots of water vapor present in the atmosphere, then you're going to feel very humid and you're going to feel hot and sticky. However, if you have hardly any water vapor in the atmosphere, you'll actually feel very, very dry, to the point that you're uncomfortable, to the point where your palms may be really dry, the inside of your ears are dry, the inside of your nose is dry, and so forth. So it's nice then to be in a weather situation where the humidity is just right, where you're not either too humid or less humid. The amount of water vapor in the atmosphere then is dependent on air temperature. And so this is a huge factor when discussing and describing humidity, meaning that the warmer the air parcel, and when I say air parcel, I'm talking about an air pocket that's within the atmosphere. And the warmer the air parcel, the more water vapor that can be contained in that air parcel. The colder and cooler the air parcel, the less water vapor that can be contained in that air parcel. So let me repeat that again, because this is a very important concept to understand with regard to humidity. So again, humidity represents the amount of water vapor in the air, and it's very dependent on temperature. The warmer the air, the more water vapor it can hold. The cooler the air, the less water vapor it can hold. So the next question is, how is humidity measured? How do you know how much water moisture or water vapor is in the air? And that's based on the concept of relative humidity. And relative humidity, which is symbolized as RH, is measured by comparing the amount of water vapor in the air. So we're looking at the current amount of water vapor in the air, and that's compared to what that particular air parcel can hold depending on the temperature. So it's a comparison between amount of water vapor divided by how much that air parcel can hold before it can't hold anymore. And so we're going to use the term saturation, meaning that when the air cannot hold any more water vapor, in other words, it's full to the brim, we would say that air is saturated. So now let me repeat relative humidity and what that means. So again, it's relative humidity compares the amount of water vapor that's currently in the atmosphere compared to what the air can hold before it becomes saturated. And when we use that word compare, then we can put it into a mathematical equation. So we're going to say that relative humidity is equal to the current amount of water vapor divided by what that water or what that air parcel can hold before saturated. Now let's look at dew point, and how does dew point relate then to relative humidity? So dew point is a point at which there is a temperature that the air parcel cannot hold any more water vapor. So instead of saying dew point, it really should be called dew temperature, because dew temperature, again, is the point or temperature at which relative humidity is 100%. And by the way, backing up a little bit to relative humidity is always measured in percent. So if we have 100% relative humidity, then we would say that that air parcel is saturated, it's full. And so again, dew point describes the temperature at which that air parcel is in fact at 100% relative humidity. So dew point and relative humidity are very relational. It has a relationship between dew point and relative humidity. So now, when you get a chance, you should get on your smartphones and you should look up what is the relative humidity for Bakersfield, and what is the temperature for Bakersfield, and what is the dew point. All of those have an integral relationship. Because when relative humidity changes or the air temperature changes, that changes dew point, that changes relative humidity. So this next slide is a slide that shows you how to calculate relative humidity. So we're just going to kind of go through this slide because there certainly will be a couple questions on the exam that will have you calculate relative humidity. And I believe there's one on the study guide. And in fact, on your work packet, I think there's a couple of them there. So again, we said earlier that relative humidity equals the amount of water vapor in the air, the current amount, divided by, so here's the amount of water vapor in the air, current, divided by the amount of water vapor the air parcel can hold before saturation. So for my example, I'm saying relative humidity, I currently have 12 grams of water vapor in the air. That's been measured, 12 grams. And the air, given the air's temperature, which is not listed on here, but this particular air, given its temperature, can hold 20 grams of water vapor before it becomes saturated. So if I only have 12 in there and it can hold 20, then we would say that the relative humidity would be 12 divided by 20, and that's going to be 0.6, but we're going to make that a percent, so we're going to multiply it by 100, and that becomes 60% relative humidity. So certainly then, the higher this number becomes, if it becomes 60, 70, 80, 90% relative humidity, now we're going to get into very muggy type conditions. We're going to get into conditions that we talked about earlier with respect to humidity. Conversely, if this number becomes 50, 40, 30% and gets lower and lower, then we're certainly going to have dry conditions. So the question then is, what happens when the air reaches relative humidity 100%? In other words, if I take this 12 grams and I now make it 20 grams, which would be 20 divided by 20, which is now 100% relative humidity, what happens? Well, it's kind of like a glass of water. You fill the water to the very, very, very top, which means that in this case, the air parcel is filled to the very, very, very top. And if you try and add more water, it's going to spill. So in this analogy, once the air is saturated with 100% relative humidity, then it's not going to take any more water vapor. And so then condensing begins and we have liquid water. So typically when it's raining outside and it's got liquid rain, or typically in a cloud, for example, you're going to be very, very, very close to 100% relative humidity. Now, my suggestion here is to practice calculating the percentages of relative humidity by following this formula. And once again, I asked a question in the previous slide, but take some time and get on your phones and find out what the current relative humidity for Bakersfield is, the current temperature, and the current dew point. And by the way, if the dew point, for example, I'm just giving an example here, for Bakersfield, let's say is 48 degrees. I'm just giving that as an example. If it's 48 degrees and the current temperature is 60 degrees, what does that mean? That means when the sun goes down, it means that the air temperature is going to get cooler and cooler and cooler, which means relative humidity is going to go higher and higher and higher. Finally, if the temperature reaches the dew point of 48 degrees, at that point, the atmosphere is going to begin to condense and will be at relative humidity of 100%. This example here is just another example to kind of show the relationship between relative humidity and dew point, for example. So for our example, we're going to allow the water vapor, which is the blue circle, to remain the same. In other words, the water vapor content or volume does not change. And what we're going to do is we're going to watch what happens to relative humidity as the air temperature gets warmer and warmer. So in our first example, we are at 10 degrees air temperature. And in the example on the diagram, it's showing you that this blue circle is completely covering up the yellow circle. In other words, the yellow circle is the air, and it is behind the blue circle. This means that this air at 10 degrees, which would be dew point for this condition, is now fully saturated. And we come down here below that, and we are at 100% relative humidity. All right, so now let's allow the air to warm. And remember, the blue circle is not going to change. The water vapor is not going to change. So we allow the air to warm. And as the air warms now, it expands. So the air is bigger. And now it can hold more water vapor. But because we kept the water vapor normal, we're showing then that what happens to relative humidity? It has dropped. And they just put 52% there for a calculation. But generally, it's going to drop. So as temperature rises, relative humidity decreases. So now let's allow more temperature to heat up the air. And now we go from 20 degrees to 30 degrees. And now the air warms up even more, again, keeping water vapor constant. Then what happens is the air can hold more water vapor. It has this much water vapor. And again, relative humidity goes down. In this case, they put 28%. So the point is, as temperature rises, relative humidity goes down. And then, of course, the opposite happens. As temperature lowers, relative humidity goes up. And this is a really good graphical example of what happens during the day. So envision the sun goes down, sun's been down for quite a while, and now the sun begins to rise first thing in the morning. And by the way, right before the sun rises, that's usually the coldest part of the day, right before the sun rises. Not at 12 midnight, but right before the sun rises. And so this scenario here would represent right before the sun rises, the coldest part of the day. And that's where relative humidity is going to be the highest. And that's why when you wake up in the morning and you walk outside and you say, wow, where did all this water come from? And somebody says, that's dew. And that's where that comes from. Because by that time in the morning, the atmosphere has reached dew point. Then during the day, the sun comes out, starts heating up the air. And by mid-morning, it may be in this scenario here, you should be able to watch the relative humidity go down. And actually, by 3 or 4 o'clock in the afternoon would represent this example where my arrow is. And that's where relative humidity would be the lowest. And so really the warmest part of the afternoon, again, is not 12 noon, but more around 3 or 4 o'clock in the afternoon. So relative humidity would be the lowest in the day and the highest in the morning. And so this is a really good example that illustrates that relationship between a dew point and relative humidity. Okay, so let's shift gears a little bit and talk a little bit about the greenhouse effect. And by looking at this first picture here, this picture is a graphical picture showing that the Earth is nestled or confined inside a glass greenhouse. And from your experiences, a lot of folks understand that typically if you're in a glass greenhouse, the temperatures are much, much warmer on the inside of the greenhouse than they are on the outside of the greenhouse. And so in these next couple slides, we're going to look at how a greenhouse works. And then we're going to take that analogy of the greenhouse and look at the relationship between the glass greenhouse and looking at how the atmosphere warms our Earth. So typically then we're looking at a glass greenhouse. The sun rays are going to enter the greenhouse. And remember, by the time that the sun rays reach the Earth's surface, we've got visible light, a little bit of ultraviolet light, and certainly long wave energy. And so as the shorter wavelengths of visible light and UV light enter the glass house, it has to pass through the glass. And upon passing through the glass, the molecular makeup of the glass itself will have a tendency to make the wavelengths from visible and UV radiation into longer wavelengths. And so at this point now, we've probably moved into the infrared type wavelengths inside the glass greenhouse. So as the infrared wavelengths go inside the greenhouse, then they try and get out, but basically they're trapped. They can't exit the glass in the greenhouse. So what happens inside the greenhouse? The greenhouse then begins to warm up. And as it warms up, temperatures get higher. And I'm sure we've all experienced this process to some degree, especially in the summertime of Bakersfield. You drive your car to the Big K, or you drive your car to a parking lot. You roll up all the windows, you get out, you go do what you need to do, and then when you come back to your car and you open up the car door, how hot is it in there? It's pretty doggone hot. It's much warmer inside the car than the outside of the car. And that's directly related to the fact that these wavelengths have been converted and changed into longer wavelengths. So we're going to take this greenhouse process now, and we're going to apply it to the Earth. And before we do that, we need to talk a little bit about some of the composition of the Earth's atmosphere. We already talked about it: 78% nitrogen, 21% oxygen, and then there's other. And that other, in many cases, come in the form of greenhouse gases. And greenhouse gases are molecules that are absorber of radiation. So they absorb radiation and then they counter radiate it back to the Earth's surface. And so some of the common greenhouse gases is methane, which is trace amounts of methane, and then nitrous oxide, trace amounts of nitrous oxide. And probably the two important greenhouse gases that make the news and folks talk about, of course, is carbon dioxide. Carbon dioxide represents only, though, 0.03% of carbon dioxide, so it's very, very small. It's not in high concentrations at all for the Earth. And then water vapor, believe it or not, water vapor is concentrated at about 0.07%. And in fact, if you look at the difference between carbon dioxide and water vapor, water vapor is almost twice as more concentrated in the atmosphere than carbon dioxide. And in fact, water vapor is a much better re-radiator of infrared radiation back to the Earth's surface, even than carbon dioxide. So this is a diagram now that shows how the greenhouse effect works to keep our atmosphere warm / cool. So it keeps it habitable for human life. And so we're going to go through the process of this greenhouse effect. And what your job is to equate, or how does this process fit in with the analogy of the actual glass greenhouse we looked at earlier. So again, we're going to go through this process, and then you try and say, okay, this is how, again, this process fits with the greenhouse. So we're first going to take our sun, and we're going to allow the sun to radiate radiation. And again, recall that by the time the sun's electromagnetic spectrum reaches the surface, we really only have visible light and a little bit of UV radiation. So it makes contact with the Earth's surface, both land and water. And then once it makes the contact with the land and the water on the Earth's surface, the land and water converts it to a longer wavelength, which is the infrared part of the wavelength. And then as that infrared heat and wavelength rise in the Earth's atmosphere, it comes in contact with greenhouse gases. And as it comes in contact with greenhouse gases, and in this case I put carbon dioxide, then the greenhouse gases absorb the infrared radiation and then counter radiates it back to the surface. And so this would be the infrared rays being counter radiated back to the Earth's surface. And as it returns, then we can say that the atmosphere begins to warm. And so this is a continuous cycle that takes place, and it is a natural cycle on Earth that takes place. So the question is, what part of this process then is analogous to the greenhouse that we showed in the earlier? And most students will come to the conclusion that the surface of the Earth probably acts as the glass of the greenhouse, because remember, the glass of the greenhouse changes the shorter wavelengths into longer wavelengths. And so that's what the surface does. And also the glass can be somewhat analogous to the greenhouse gases as well, because the glass likes to trap the infrared radiation rays back into the greenhouse, and in this case, back into the atmosphere. A lot of folks will describe and use the word trap, and folks will say that the longer wave infrared wavelengths have been trapped by the greenhouse gases, re-radiated back into the surface. So again, your job as you watch this presentation is to learn in your own words how the greenhouse effect works. Because I can guarantee you, in terms of our exams, you may see a essay question that will ask you, how does the greenhouse effect work? And there you can see the atmosphere heats up. So the other question is, what do you think the role of water vapor is in the atmosphere? Because it's also a greenhouse. And so in most literature that looks at global warming will blame basically carbon dioxide as the main greenhouse gas component that heats up the Earth's atmosphere. But I say we need to pay attention to water vapor because, again, water vapor is almost 2 times more concentrated than carbon dioxide. So my question for the pundits that look at carbon dioxide as the culprit for global warming in terms of the atmosphere is, what does water vapor role play? How come there isn't articles that really talk about what water vapor does? Again, it's 2 times more concentrated. So do we need the greenhouse effect? And by the way, GHE means greenhouse effect. And we could say, well, would global temperatures be minus 15 degrees without the greenhouse effect? And the answer is absolutely yes. The greenhouse effect is very natural. We need the greenhouse. Again, if the greenhouse effect was not on Earth, then again, global temperatures would be very, very cold. We certainly have a different type of existence on this Earth. And does the greenhouse effect act as a blanket keeping the Earth warm? The answer is absolutely yes. We just explained that looking at the other 2 checks. Now, the other question that I like to bring up is the greenhouse effect considered a contributor to global warming? And really, the answer is no. And I say no because, again, the greenhouse effect is natural and we need the greenhouse effect. And if I get into a debate with somebody and they start blaming the greenhouse effect for global warming, I immediately shut that conversation down because I don't believe that person understands really what the greenhouse effect is. And so the global warming debate considers carbon dioxide. And is the atmosphere warming? Yeah, the answer is yes. I don't think alarmingly, but it is warming. So the question is the increase in the global atmosphere warming due to carbon dioxide natural, or is the increase in carbon dioxide man-made? And so really that's what the debate behind global warming issues is: the CO2 natural or is it man-made? But again, as mentioned earlier, I don't really ever see folks talking about the role of water vapor because it also is a very powerful greenhouse gas. So those will be some interesting questions to look into. And as educated folks, I believe you should be aware of what the greenhouse effect is and be able to, at some point, maybe look into literature that covers carbon dioxide.